everybody have a good Easter? No? Fair enough, me neither. Actually, no. My Easter was good. Didn't get much work done, obviously. Yeah. Do you want to crack any jokes?
I've got no jokes.
I have a joke. 2 men walked into a bar. Do you get it?
Is that the joke?
That's the joke, get it?
Well, they're going out for a drink.
No, because I like walk into a bar, like
Oh.
hit the head.
That's actually quite good.
Yeah. So it's like
I actually think that's quite good.
it's actually it's a meta joke because it's like a joke about a joke, right? Because it's like a common joke, but you make a joke about that joke. So it's a meta joke. Yeah. So.
You're right, we clock it.
No. People want to know. Okay, I shall start. Okay. Thank you everybody for coming. So I'm going to be doing a little introduction to the Go programming language, and then on top of that, we're going to be doing a bit of concurrent programming. So if you don't know what concurrency is, it's essentially a way of writing programs such that components of the program can be run independently of each other. But we'll get more into detail of that later. So, why learn Go? The main point is that it's quite easy to learn Go because it's such a simple language. It's got only, I think, 25 keywords. They might have added one or a couple. But like for example, C++ I think has over 100 keywords. It's a massive language, whereas Go is really, really small. And it's exciting in the sense that it's not that exciting. It gets the basics really, really well. Like the basics are amazing, as you'll see. Because it's so simple, generally there's only like one way to write something. And that's good if you're working in a team, because if you're working in a large code base, you want to be able to understand the code you're reading. You don't want each bit of code to have like its own little dialect. You want everybody working on the code to write code that looks the same, so when you revisit code, you can read it. Simple. And so obviously this is because it's not that expressive, which is obviously also a con, because it might mean you might need to write more lines of code overall compared to some other languages. The other reason to learn Go, easy concurrency. If you're writing an application where without concurrency you're going to have a lot of blocking, that's just not going to be good. Like if you're writing an application that can be split up into lots of little components, for example, maybe a web server where each request is handled in its own concurrent thread, then you won't Go. And obviously, concurrency can also sometimes lead to more performance if things are being run in parallel. But when we'll get to Go routines, I'll sort of point out that that doesn't always lead to an overall performance gain. It's sort of up to the Go runtime. It's fun to write like Python, but with the performance of Java. What do I mean by that? So obviously Python, really easy to write. It's dynamic in the sense that you don't have to define the types or anything. Go, on the other hand, is statically typed, but as I'll show you, there's really good type in front, so it feels dynamic. Go is compiled, but as I'll show you, it compiles really, really quickly. So it basically feels like an interpreted language. Again, it sort of feels like Python, but in my opinion, it feels better designed as well than Python. The other reason, it's made by people who are deeply involved in Unix, with Unix and C, so it's made by 3 people, basically. Ken Thompson, who basically invented the Unix operating system. Rob Pike, who was sort of working at Bell Labs, who were the people who pioneered Unix and C, and some other guy, I can't remember his name, to be honest. I think Griesmer, maybe? I'm not sure. Yeah, so it's got an elegant design and appreciation for simplicity, which is sort of the Unix philosophy. The other reason to learn Go is the company's using it. Obviously, it's made by Google, so yeah. Uber use it, Monzo use it basically exclusively. Netflix use it in some areas, and more companies are using it. Yeah, so let's write some Go. Any questions so far? No? Cool. All right, so I'm sort of assuming, if you are following along, I'm sort of assuming you've already installed it, so sorry if you haven't. So make a file, basically. Then you need to first define a package. To be honest, I don't really fully understand the package stuff, so in general, just do package main. That's sort of more advanced stuff. So for your main function, you're going to do, so you define a function with func. And then to declare a variable, so there's a couple ways of doing it. So let's do it the most explicit way first. So basically, so you say it's a variable, then you say the name, and then you do the type. So this is how you do it in the most explicit way. And something that is a bit annoying about Go actually is if you declare a variable but you don't use it, and we try and run it, it doesn't, it errors out basically. You have to use a variable that you write, which I personally find annoying. I think it would be better if it was just a compiler warning. But anyway, so if we want to print it, we do fmt.println, and you have to import it like that, and then easy. Okay, but this is a bit verbose, and I promised you that it's going to look a bit like Python, so the alternative way of doing it is by just adding a colon, and then it has type inference. So that is equivalent. So if you have like a text editor that tells you the types, we can see that B is an integer. Okay, so let's move on to arrays. So arrays, so this is sort of like a C-style array, right? So what we're saying here is we're going to have an array of integers. We're going to fill it with the values 1, 2, and 3. But crucially, this bit here tells us the size of the array. So this is an array of size 4. So if we print this out now, and we filled it with, so see we've declared an array of size 4, but we filled it with 3 values. So you guys can probably guess what is going to print out. You know, mentally trying to figure out what's going to print. So it's 1, 2, 3, 0. And then we can obviously add a fourth element, right? Like so. Just like that. But we can't like append, so this isn't like Python, right? Because this is a fixed sized array, which is not, you know, for most things you don't really, you're going to want like a dynamic array. If we can't append to it basically. So if I do try and do like, append, so this is how you append in Go. So you append the name of the list, slice, which we'll get to, and then the element. So this just does not work, right? Like we're getting a little error. First argument to append must be a slice, so we can't append. So how do we make a slice? So we make a slice by just omitting the number, basically. So this is basically a dynamic array, similar to a list in Python or an array list in Java. And actually, I'll just show you how to. So to append. Oh wait, that did not do what I wanted. And then we can append to this. So 3. Okay. We can also append lists to lists, but you have to do it in kind of a specific way. So if we try and do this, we're going to get an error. because you can only append a value, and we're trying to append a slice to a slice. So by the way, a dynamic array in Go is called a slice, which I'll get to in a minute. So we have to do this ... which sort of tells it to iteratively, it basically tells it to iterate over the values of this slice and then do the append operation. Wait, sorry. Okay. So, but the way a slice, so one thing that's cool about Go that you can't necessarily get in, say, Python is we can get finer grained control over the actual underlying data structure that the slice is built on top of. So if we make a slice, but we're going to make this slice a slightly different way. So we're going to make it using make. So we have to define the type that we want. So we want it to be a slice of integers. We have to give it the length of the slice, which we're going to set to 0, and then the capacity, which essentially is the underlying array. So if I print, sorry, if I print this out now, it's empty. But I can append, say, 6. And we have 6 now. But the way this is working is... Where's the pen? Cheers. So the way a slice works, and if you've studied dynamic arrays, then this is kind of trivial, but the way a slice works is there's an underlying array, which is, let's say this is an underlying array of size 4, and then the slice is like a slice of it. So if we do make with a length of 0, but a capacity of 4, it's going to sort of look like this, where like this is the slice, right? And this is the underlying array. But then as we append, we're going to sort of fill out the underlying array. So we append, and then we've reached the capacity now. So if we do another append, basically Go is going to automatically allocate a new array, which is going to be probably twice the size. So the capacity will probably double. The capacity will probably double from 4 to 8. And then the actual length of the slice will probably be 5 if we do another append on top of this. So we can kind of see this actually in the code. If we do let's do it. Let's create a slice with a length of 2 and the capacity of 4. And so if we print this, you can probably guess what this is going to show. It's going to be 2 zeros, right? And we can print the length. And we can print the capacity. So the length is 2, the capacity is 4. But if we do a couple of appends, so now the length is 4, capacity is 4. Then if we do one more append, the capacity goes up to 8. So we can see the underlying array has just doubled in size, but the actual length of the slice only went up by 1. So this is cool and go. We'll come back to this later, how you can sort of optimize optimize your code. If you know how much capacity you're going to need, you can optimize that. Okay, so now let's move on to hash maps, which is something that, again in Python we sort of take this for granted. You have dictionaries, it's really convenient. But in a lot of other languages, like say Java, hash maps are kind of treated like a second-class citizen, because you sort of just treat it like any other object, which is not as nice really. Like if you want to initialize a hash map with a bunch of stuff, it's just not as nice. Where in Go it's like a native type. So if we make a map, so we say map, and then we say the type of the key and the type of the value. And so we're going to do it like this. Hi. And then okay, and that's how you do it. So again, so that's super similar to Python, right? And then you can add more stuff if you want, but we're not going to do that. So if I want to print that out, we'll see. I think you kind of understand it at this point. Yes, it's super nice. And one thing actually I've kind of failed to mention is we're just running go run and then the name of the file, right? So again, this feels like an interpreted language, but behind the scenes, it's compiling the Go into machine code, basically, and then executing it. So we could do, I think, go build, right, and then we can execute teach, right, and it does it. But most of the time you don't really want that. You just want to do go. You just want to run it. And it compiles so quickly, it does just feel like an interpreted language, which is so nice in terms of being able to iterate quickly and experimenting with your code. So hash maps, I'll quickly just show how to loop over something. So let's make a string. Actually, let's do a string. And then to loop over things. So there's only one loop type in Go, and that's the for loop. Every single loop you do is a for loop. And it has a range keyword, which in some ways is kind of the opposite of Python's range, which is kind of interesting. So if we do range str1, so it's basically a nice bit of syntactic sugar, where it gives you the index and the value. So you can think of it kind of like the enumerate in Python, actually, thinking about it. If you don't want the index, by the way, you can just do the underscore. But we want the index, because why not? Let's do I and C. So what you're going to notice here, so we're looping through this string. It's going to go character by character. What you're going to notice that it actually prints the integer, Unicode of the string. And yeah, that's kind of an interesting thing about Go. I think it's because, I'm not entirely sure why it does it in this case. I don't know. I think it's because Go has support for Unicode out of the box. And that kind of does complicate things in the sense that a character is not necessarily a byte. A character could be many bytes. It could be also many symbols joined together, because Unicode is very odd. The range operator does kind of hide this, though. Say if you do have a special character that takes up multiple bytes, I believe that the range does kind of skip over those intermediate bytes. I could be wrong on that. Probably worth looking into. But if we do want to just print the characters, we use printf. This is kind of, you can kind of see the C influences in this. But we're going to format it as a character, and then print the character. And then you can see the actual characters here. Okay, but you guys came here for some concurrency, so let's do some concurrency. Actually, which way should I do this? Let's make a function called computation. That is we're gonna have like an imaginary computation that takes a long time. So we're gonna import time, and we're gonna sleep for for 3 seconds. And then for now, that's all we're going to do, because we don't really. I guess we'll return. We'll return a number. I don't know. I guess we should probably. We'll just print for now. Okay, so we're going to call this computation in our main function, and then we're going to do another computation it's going to take 2 seconds, and then we're going to say right, so you guys can probably guess how long this is going to take. 1, 2, 3, done, 1, 2, done. Okay, so it takes 5 seconds. But what if the computation, what if the output of this computation here is only really needed down here, right? And is not really needed in this bit of code? One thing we could do is we can actually run it concurrently, right? So in Go, there's a keyword, and the keyword is Go. And what Go does is it'll run this function in a Go routine, and a Go routine is run concurrently to the other threads, to the other Go routines. And concurrently doesn't necessarily mean in parallel. It doesn't necessarily mean it's going to be run at the exact same time. It just means that the execution can kind of be done independently. So let's just do done 1, done 2. So if we do that now, we're going to see that we get done 1 and then it finishes, right? Why does it finish? Because we want done 2 to show up, right? So we're basically, what's happening, we're saying run this in the background or in another Go routine, which isn't always in parallel, as I've said. But to be fair, in general, on my computer, it's always going to be in parallel because I have a lot of cores. So it's going to sleep for 2 seconds. It's going to do done 1, and then it's going to reach the end of this code, right? And then it's going to finish. So it didn't wait. It didn't wait for this computation, which is bad. So what we want to do, and also we want to be able to communicate. We want to be able to communicate the output of this computation to like our code down here. So the way we do that is through a channel. And so a channel in Go is the way that different Go routines communicate with each other. So let's make a channel. So we're going to call it chan, and the channel is going to send float 32s over it. So that's a floating point number. And we're going to pass it into computation. And so we're going to accept chan float 32. Okay, so what we're going to do is after we've done our computation, we want to send the output of the computation back to the Go routine that called computation. So we're just going to make a random, this just so I can show you how you do random numbers. So let's just make a random number. We're going to give it a seed of time dot now. And then we're going to, so down this channel, which we've passed in here, down this channel, we're going to send a random number. So, I'm not sure if this makes sense right now, but it will make sense, I promise. So here, we want this answer because we need it now. We need it for some other computation, let's say. And then we want to print this. Okay, so what is happening here? What is happening here? Let's compress it so we can see more. So we make this channel up here, and then we pass this channel in, right? We do our long computation, and then we send the computation down the channel. But remember, this is all happening concurrently. So because we're saying go do this computation in the background, right? So we're sleeping for 2 seconds, and then we block here. We block until something is received from this C1 channel. So we're going to do this computation. We're going to block here until we get C1, and then we're going to print ants. So how long do we think this is going to take? 1, 2, 3. So it only takes 3 seconds now. So we've shaved 2 seconds off because these things are happening in parallel. But what's so cool is just how simple it was to make like a parallel program. Like this isn't trivial in a lot of other languages, but in Go it's kind of trivial. And channels help you sort of sync up these computations between your various Go routines, and so that's very cool. So that's basically the bulk of the Go that I'm going to teach you. What we're going to do now is we're going to put some of this Go into practice into something that's actually useful. Well, yeah, something that is actually useful, which is the merge sort algorithm. So we're going to create an implementation of merge sort, and we're going to make it concurrent, which hopefully will increase the performance. And so to explain merge sort, my lovely assistant Marlin is going to explain it, sort of give you the intuition behind merge sort if you haven't done it before, and then we're going to put it into practice with into Go. So thank you, Marlin.
I'm going to be explaining to you what a merge sort is. So we're going to take between the numbers 2 and 9 some unsorted integers, and then we're going to sort them. So the idea of a merge sort is to take some unsorted integers and sort them such that they end up ordered, right? So I'm going to explain it by using the whiteboard. So what you should know is that the merge sort is a recursive algorithm, which means that it uses the divide and conquer philosophy, where you take a big problem and you break it down such up until you have really, really small sub-problems that you can solve easily. Let me see if I can lift this up. Okay, cool. Okay. I don't think I can lift it up. Okay, I'll use this one. This one's higher. I'm just making sure everyone can see that, right? I was trying to bring it up higher so that everyone can see. Can everyone see that? Okay, cool. Okay, so we're going to take some randomly sorted numbers between 2 and 9. 2 and 9 because I'm missing the 1 cards. That's why. You'll find out what I mean by cards soon. So we'll put a random number here. We'll call it 9. We'll put a random number here, 3. We'll put a random number here, 7. We'll put a random number here, let's do 5. And we'll put a random number here. Actually, there should be 1 in between. We'll put a random number here. We'll call it 4. Oh, that's implicitly ordered. I don't mean that. And we'll put another number here, 8. And we'll put a number here, 2. And we'll put another, I think that's it, is it? Which number I'm missing? 2, 6, yeah? All right, cool. And I'll put another number here, 6. And we should have 8 numbers. Yeah, we've got 8 numbers, right? So what the merge sort does is, the first step is to divide, right? So we need to divide this until we have small logical units, right? So the smallest logical unit here is obviously an individual number, right? So what we're going to do is we're going to break this down. So what first happens is that this breaks down. I'm going to not draw the boxes because it takes a while. We're going to break this array of numbers into two separate lists, which is going to be 9, 3, 4, 7. So as you can see, we broke it in half. I'm going to break the next part of the subarray, and we're going to get 5, 8, 2, and 6. And then we're going to keep doing this break, right? So the breaks are happening in the middle. So we break this, and we get 9, 3. Break this, we get 4, 7. Can you see that? 4, 7. And then we're going to break this, we're going to get 5, 8. And then we break this, we're going to get 2, 6. And then obviously there's another break, so then we're going to break it to 9. We're going to break this to 3. We're going to break this to 4. Break this to 7. Break this to 5. Break this to 8. Break this to 2. Break this to 6. Right? That's the first step, right? We've broken down everything into the smallest logical unit, which is an individual number, right? So now what we need to do is what we call the conquer part, right? So that means we've divided everything, and now we need to sort of bring it back together, right? So what I'm going to do is I'm going to start from these individual numbers on this board, and then conquer back to where we have 8 numbers, and they're sorted, right? So we're going to have a 9, we're going to have a 3. So these are now individual elements, they're not joined. And then we have a 4, then we have a 7.
Can we just test if this works? I think this might work.
Okay. And then we have a 5, and then we have a 8, and then we have a 2, and then we have a 6. So now we've got these individual elements. How do we pair them up, right? So what we do is we have a look at these two adjacent elements, and we're like, okay, which one comes first, 3 or 9? So 3 comes first, and then 9 comes afterwards. So they're joined, right? So now you can see we're basically the opposite. Instead of splitting, we're joining now, right? Then we have these numbers 2, 4, and 7. What do? We join them, and then we get a 4 and a 7, right? And then now what we do is we look through each array, basically from left to right. So now we have here 3, 9, 4, 7, right? So we'll focus on these elements. Which one comes first? 3. Move this pointer here. Okay, now which one comes first? 4 or 9? Then we get 4. Okay, move this pointer to the right. Which one comes first? 7 or 9? Then you get 7. So then, that pointer stays. And then which comes first? 7 or 9? And then 9 comes. And now this is equal to the length of the two subarrays. So that means that we have successfully sorted this half, right? So now we're going to sort what we have left on this side. And basically, we're going to have a look, okay, which one comes first, 5 or 8? 5. 5 comes first, and then 8 comes next, right? We kind of implicitly got that they're ordered. And then, obviously, with this one, 2 comes first, and then 6 comes next, right? Then we're going to repeat the same process. So we sort of have 2 pointers here. And then which one comes first? It's going to be 2, right? So we're going to put 2 here. Really, that should be coming from there. They're being combined. You get 2. Okay, cool. That's cool. And then we're going to move the pointer to here. And then we're going to be like, okay, which one comes first? 5 or 6? 5 comes first. Okay, then move this pointer to the right. Okay, which one comes first? 6. Okay, we've dealt with that. Which one comes first? 8. Now this is size 4. These were size 2. So that means we've complete. Now we're going to run the same conquer algorithm we've been running to join these elements on the last 2 subarrays. So we're going to join these. Okay, so we have 2 pointers. I'm going to just highlight them now to make it easier. Okay, which one comes first, 2 or 3? We get 2. Okay, move the pointer to the right on this side. Which one comes first, 3 or 5? And we get a 3. Okay, move the pointer to the right. Okay, which one comes first, 4 or 5? 4. Move this pointer to the right. Okay, which one comes first? 7 or 5? 5 comes first. Move this pointer to the right. And which one comes first? 6 or 7? Sorry, this is a bit repetitive. 6. And then, so move this pointer to the right. Okay, which one comes first? 7 or 8? 7 comes first. Move this pointer to the right. Which one comes first, 8 or 9? And then obviously 8 comes first. And then at this point, you normally realize you've gone past the size of the array. So that means that you know that you have to add whatever elements are left. So you'd add 9 here. And that's basically how a merge sort works. I'm going to show you with some cards how the merging process works. So basically how you go through left to right, left to right. So I've got 2 packs of cards here. It's probably going to be a bit difficult for you. Okay. Hopefully this works. Yeah. Okay. So I have 2 sorted lists here, right? So let us imagine we have. I'll actually make these the same. So we have element 3. We have element 4, and hopefully, oh, my hands went in the camera. So we have element 3, element 4, and element 7, and element 9, right? So this represents the left array right there, right? So that's our first subarray that we're going to be combining. Then our next subarray has 2, 5, 6, and 8 in it, right? So as you can see here, we need to combine these such that they're together. And I'm going to put the smallest element on top, just so that it's easier to see what we need to combine first. Okay, so we're going to run the merge algorithm. So what goes first? 2. Okay, what goes first? 3. Okay, what goes first? 4. Okay, what goes first? 5. Okay, what goes first? 6. What goes first? 7. What goes first? 8. What goes first? 9. And it's kind of like magic, and they're all sorted now. So that's sort of how the merging part, hopefully that was all on camera, but that's how the merging part of a merge sort works. And we're just going to show you a quick video showing you that how it's really working in basically units that are of, like basically each of a half of the unit that they came from. So if you have a look at the video, you'll probably notice the trend of this divide and conquer, splitting into 2 and then conquering back up in basically blocks of 2.
Oh, there's no audio. Oh, well.
So as you can probably see from that video, you could see how it was working in blocks of 2, right? So basically it was working in halves, and then it was combining these smaller sorted arrays to build bigger sorted arrays. Anyways, yeah, that's it.
Another thing you might have also noticed is how it totally could have been done more in parallel. Like, because you saw it was sort of did it blocks left to right. But if you could do those blocks at the same time, then we could save time, basically. Okay, so let's. So thank you, Marlin. Let's do this in Go. Worried the mic situation. I think the mic situation should be all right. Does it sound all right coming from here? Okay, perfect. Okay, so let's make a new file, call it mergesort.go. So again, package main, never mind. Okay, and so first of all, let's just sort of make a list that we want to merge. So again, we're making a slice here. Let's do it like 5, 2, 7, 10, 2, 1, 9, 3. Okay, so we've made our list, and then we want to sort it. So let's make a function called merge sort. Oh, actually, one thing about Go, this is my understanding, I could be wrong, is that if you have like a public function that you want to be able to be called from other source files, you make the first letter a capital letter. So this is a public function that can be called from other source files, right? Because we want other people to be able to call the merge sort. And we're going to take a list, which is going to be a integer slice, and it's going to return an integer slice. Okay, and so in our main we want to call this. So we're going to make a variable called sorted, and we're going to call merge sort on our list, and then we're going to do an fmt.println the sorted list. Okay. Yeah. So as Marlin said, so we sort of keep breaking it down until we reach the base case. And what is the base case? The base case is when the size of the slice is going to be 1 or less, I suppose. So if we can do if len of list is less than or equal to 1, then we are going to simply return list. So this is how if statements are done in Go. If it wasn't, kind of trivial. And otherwise, we're going to want to sort of split the list in half. So we're going to get the halfway index. So we're going to do the length of the list divided by 2. So in Go, because the length is an integer, right? If you do a division on an integer, it's going to be an integer. So we're doing an integer division, so you don't have to worry about it there being any like decimal points or anything, which in my opinion is quite nice because integer divisions are quite useful. And then we're going to make 2 slices. So this probably isn't. Oh, is it because it's gone? Wait, I don't know why that happened. All right. So we're going to make 2 slices. So these are the slices we're going to split it into. This probably isn't the most efficient way of doing it. I guess if you did it all in place, it would be more efficient, but this is more easy to follow, I guess. And what we're going to do is we're going to do run merge sort on the split list. So we're going to do it like this. Again, this is super similar to Python, right? So we're taking the we're running merge sort recursively on half of the list. So this is the first half of the list. So we start basically at index 0 and we go up to the halfway point, which we've defined here. But we don't need that. We can just do it like that. Why are we getting an error? Declared but not used. Yeah, fair enough. And then what we want to do, once we've recursively done all this, we've done this merge sort, it's going to keep recursively calling merge sort until we reach the base case, and we keep building these things up. And then what we want to do is we want to merge these lists together. So we're going to return the merge of S1 and S2. So we need to make a merge function now. So we can do func merge. So we're going to make this one private because I feel like you don't really need the merge by itself. So we can do L1, L2, and it's going to return a singular integer slice. We could do this with generics, but I decided not to. So what we're going to do is we're taking two lists, we're merging them into one. One trick that I sort of alluded to earlier that we can use now is we can make a slice of a certain size. So we're going to make an integer slice with the length initially of 0, but we're going to make it with the capacity of the length of L1 plus the length of L2. So what this means is that the underlying array of this slice is never going to have to be reallocated. It's going to be allocated once with this capacity. So this is just a little efficiency gain. And then we're going to do the merge algorithm that Marlin outlined, which essentially is to have a pointer to the beginning of each list and iteratively select the smallest one and then increment the pointer. So to do that, we're going to do a for loop, because as I mentioned, there's only one loop in Go, which is a for loop. So by the way, if we wanted to make like a while true, this would be the while true. So you would do your stuff and then you would break eventually. So that is a while loop in Go. But other than that, and I showed you the range operator, but other than that, it's kind of like a sort of C, JavaScript, Java loop where you'll have your semicolons. So it'd be like I equals 0, I less than 12, I plus equals 1 or whatever. But we don't actually need these things. All we need is the actual declaration. So we're going to say I and j are equal to 0 and 0. So this is how you do a multiple declaration in Go. And then for the actual incrementing and breaking out, we're going to sort that out ourselves. We're not going to rely on the loop for that. So, and I'm going to sort of write this kind of backwards to how you would intuit it. So if this doesn't make complete sense, I apologize, but it will make sense at the end. So if I is at the end, right? So if the pointer has reached the end of the list, then we know just to add the rest of the other list, if that makes sense. So if I has reached its length, then we're going to append the rest of the other list. So to do that, we're going to start at j, and we're going to go to the end of that list. But remember, you can't append a slice to a slice. What you have to do is you have to sort of iterate through that slice. So you do it like that, and then we can break. And then we basically do the same thing, but for j. So else if j equals, do that. I hope I haven't, yeah, okay, that looks about right. And then else if, so the other case now is when we're comparing the two values and one of the values is smaller than the other, so we're going to add that value from one of the slices. So else if the ith value of L1 is less than or equal to the jth value of L2, we're going to append that I1 value, that L1 value. So s equals append s of L1I, and then we want to increment I, and then else. So the other case is that we want to do the same thing but for j, right? So so that's basically it, right? So these are our pointers that sort of Marlin alluded to, and then we compare the elements here. We append the smallest element, and then we increment the pointer. And obviously this else is just for the other case where we append the other one. And then this is when we've reached the end of one of the pointers, then we just add the rest of the other list, and then we break. So I hope that makes sense. And then obviously the last thing we need to do is we need to return s. Oh. Okay. And so I think we're done actually. I think this is it. I think this is our merge sort. So let's just test if it works. So keep this in mind. I hope it works. Go run. Okay, there we are. But obviously, this is just running. What's the word? In sequence. But we want to be able to do this in parallel. And what you might have noticed is this, right? Currently, we're doing this entire half of the slice, and then doing this entire half of the slice. What if we just did these things at the same time? We could save some time. Obviously, there's these, for the merge to take place, these two need to be finished. So it's not like an infinitely better. It's not going to be like infinitely faster or anything. Like these two do need to be done for this. But if we did do these two at the same time, we could get a considerable speed up. On my system, when doing like really large data sets, I've noticed I get about a 3x increase in performance. But I do have I think my laptop is 16 cores, so obviously the fewer cores you have, the less of a boost you're going to get. But yeah, so let's do that. So what we want to do is we want to do something sort of like go merge sort whatever, but we can't actually do that right now. What we want to do is we need to wrap it in a function. So we need to do go. Well, okay. So how do I explain this? Yeah, we'll wrap in a function. So we're going to do go func. So we're going to do this is an anonymous function. So this is how you do an anonymous function in Go. So we're going to do that, and then so this is how you sort of define an anonymous function. But we also want to run it. So we add this at the end, because let's say if it had a parameter here, something, you need to pass in the parameter here, if that makes sense. So I want to do that there. And we also want to do it here. Right. But what you might be able to predict... Actually, let's run this and see what happens. That is what happens. I don't know if you could guess why, but what happens is... So we declare these empty and not even like initialized slices. We say, go do this in a Go routine. So it goes straight to this line without this having finished. We say, go do this, right? And then it goes straight to this line without having finished this, because these two things are currently running in the background. And then we run this merge. And remember, these are currently like uninitialized slices. So it's going to pass in these uninitialized slices into merge. And then it's just going to like exit out of this basically straight away. Like there's nothing to do because there's no values in there. So it's going to return S, and then that's going to be empty. So that is how we end up with this empty thing. So what do we need here? What we need to do is we need to block here, right? We need to block here to wait for these two things to finish. So how do we do that? Go has something called a wait group, like wait group. So let's get that in, right? So we'll do var wg. And we need to get the sync module dot wait group, and then like to be fair, this is quite simple if you think about it. So all we're doing is all we need to do is do wait group dot add to, and then we want to do wait group dot done here, which decrements it, and then what we're going to do here is wait group dot wait. So, what's going on here? So we're adding 2 here. We're doing this go routine, which runs concurrently, runs this, and then when this is finished, this line of code is executed, which decrements the wait group by 1. And same for here, it decrements it by 1. And what wait does, it blocks here until the wait group reaches 0. So we can kind of see this in the... So adds delta, right, done. Decrements the wait group counter by 1, and then wait blocks until the wait group counter is 0. So this is like a super simple thing, and it's basically solved all of our problems. So it still works, but now it runs things concurrently. I I might as well show you guys this keyword as well, where we can just add defer. And what defer does is it runs this line of code when we sort of reach the end of the block of code it's in. So even though we have the done up here, this line of code is only sort of fired down here, if that makes sense. So that can be quite good. Say if there's just loads of lines of code, you know, you're writing loads of code and you forget to add in the done, that could be kind of annoying. But if you just add it in straight away, because you know that you're going to need to sort out this wait group stuff, you might as well just add it at the top. And yeah, that is it. So we now have a concurrent merge sort. And remember, concurrent doesn't always mean it's going to run in parallel. So you might be disappointed, if you run it on your computer, you might be disappointed that it's not going any faster. And that's because it's up to the Go runtime. It's up to the Go runtime whether it's going to run on separate cores or not. It might just context switch between the Go routines. And in that case, you're actually going to end up with worse performance, right? Let's say if it does just execute on one core, but it constantly context switches between all of your Go routines, it's going to be slower than if you didn't do the Go routines to begin with. A big reason for the Go routines is just, say if you have like a blocking input-output, you can then do other stuff while it's blocking without needing to, without like just staying on that blocking thing until something else happens. So concurrency is useful even if it's not in parallel, mainly for like input-output stuff, which is sort of what Go was largely designed with in mind. But in this case, it does actually give me big performance boosts, so it's very cool. And again, like it's what I love so much is just how trivial it is to turn it into something that runs concurrently. Like that's all we had to add, and then it just works. Which I feel like in any other programming language, maybe you could do it in the same number of lines of code, but it's going to feel a lot more faffy. Whereas here it is not. It's trivial. Yeah. So that's basically it. So if you guys want to do any further study, these are some good resources. I especially recommend this one, Concurrency in Go. It sort of goes more in depth on concurrency and sort of talks about sort of like worker pools where you might have a bunch of work to do and then Go routines will sort of fetch some of the work and then announce when it's finished. So it's very cool. This one's kind of fun, this Go Proverbs. It sort of gives advice on writing Go in a very sort of idiomatic way. It was made by one of the people who made Go. This is also sort of a speech by one of the guys who made Go who sort of emphasizes that concurrency isn't parallelism. So you shouldn't always expect it to just like be faster. And then Learn Go in 12 minutes is, we've kind of covered most of the stuff, so you don't really need to watch that. But it's, anytime you want a refresher in Go, I would recommend watching it. Yeah, and that is the other cool thing. Like, we have covered a decent amount of Go in this hour. And it's kind of amazing how within like a few hours, you can be pretty productive in Go, which is really a testimony to how beautifully it is made and how intuitive it is. Like, I think a lot of the things that you would have seen today, you would have sort of intuitively known. Like, it is a very intuitive language. But yeah, so thank you for attending, everyone. You can get your attendance certificate. You can put it on your LinkedIn or whatever if you want. But yeah, thank you for coming, everyone.
Thank you so much. We have a few updates. Next week, there is going to be next to next week, there is going to be a end of the year social on 9th of May. It would be a movie night. We are showing social networking, okay? And on 10th of May, as you know, Google I/O is being hosted. So we have organized a watch party at 6 p.m. in Uniplace. If you are free, you can come we will have a lot of food there, pizzas and desserts, everything. We have got a huge budget. And we also have swags in that. So if you want to take a break from uni studies and come while returning back to home, you can come and have some snacks and watch a watch party for a while. We will show keynote of Google I/O, and yeah. And after exams, if you are still here, we are organizing a Google I/O extended where we are going to call a bunch of Google speakers who will talk more about Google I/O in a detailed way. So yeah, feel free to come. Thank you so much for coming. Thank you so much for
Thank you.
doing workshop.